Hello guys, and welcome back to my channel, Visual Learners, and in this video we're going to talk about another version of YOLO in the YOLO family series called YOLOR. Some of the main points that we're going to cover in this video includes an introduction to the YOLOR model. Second, we're going to talk about the creators of the model. Next, we're going to see the distinction between two main points that were mentioned on the paper of YOLOR called explicit and implicit information. On the fifth section, we're going to talk about how to unify the explicit and implicit information to create a unified YOLOR model. On the next section, we're going to discuss about how to model implicit knowledge. And we finally conclude by talking about the YOLOR overall architecture and the results from the model. First, let's see an introduction about the YOLOR model. We've seen previously that YOLO stands for You Only Look Once, but YOLOR is slightly different. YOLOR stands for You Only Learn One Representation, which is completely different from the previous acronym. Not to be confused with YOLO versions 1 through 4, because the authors are completely different from the previous versions of YOLO, and it is the state-of-the-art machine learning algorithm for object detection, different from the YOLO v1 to YOLO v5 model due to the difference in authorship, architecture, and model structure. At first, this does not make much sense, but after reading the paper or this article, you will see that the title wraps up what it's about quite nicely. So, you only learn one representation is a technique that is completely different from the techniques that were deployed on the previous versions of YOLO. And to set it apart, they gave it a different name. Next, let's talk about the creators of the YOLOR model. The authors of the YOLOR model include Qianyao Wang, Aihao The, and Hongyuan Mark Liao. However, the previous versions of YOLO implementations have been created by Joseph Redman and Alhi Farhadi from YOLO v1 to YOLO v3, and starting from YOLO v4, it was implemented by Alexei Bukovsky. And the authors of YOLOR represent the Taiwanese Institute of Information Science, Academia Sinica, and Elan Microelectronics Corporation of Taiwan. Next, let's talk about how the YOLOR model works. We already know that humans are able to learn and understand the physical world based on vision or hearing, such as explicit knowledge, but also based on their past experience, which is called implicit knowledge. Therefore, humans are able to effectively process entirely new data by making use of abundant experience from prior learning that is gained through normal learning and the information that is stored in the brain. So humans, in order to make judgment or in order to decide or learn something new, they use a combination of explicit and implicit knowledge. And explicit knowledge generally means something that is associated with our senses. So if we perceive something using our vision, hearing, then that information is known as explicit knowledge, something that we learn from our new information. But implicit knowledge is something that is ingrained into our brain, or something that we have previously learned and that could be applied in the future. So based on this idea of how humans learn, the YOLOR research paper describes an approach to combine both explicit knowledge, which defines as learning based on a given data and input, with implicit knowledge that is learned subconsciously. Therefore, the concept of YOLOR is based on encoding implicit and explicit knowledge together, similar to how mammalian brains process implicit and explicit knowledge in conjunction with each other. So the unified network proposed in YOLO-R generates a unified representation to serve a variety of tasks all at once. Now, let's delve into the specifics of explicit and implicit knowledge so that we can understand what they mean. So explicit knowledge is known as normal learning, or things that you learn consciously. For example, if I walk up to you and say that this is a dog, you'll be like, that is a dog. So if I give you an object and a label, then you tend to make association between the label and the object. So in the future, when I show you a picture of a dog, then you automatically say that is a dog. So explicit knowledge is given to neural networks by providing clear metadata or image databases that are either thoroughly annotated or well organized. So in the same way that humans learn, a machine can learn by giving it data, clear metadata, and image representation of an object so that it can learn to make association between the label and the object. So the data must be thoroughly annotated and well organized so that the machine can learn to make the association. So explicit knowledge can be thought of like flashcards for the machine learning model, with clear definitions and pictures or inputs corresponding to those images. So it's kind of like giving a flashcard to the model so that it can remember the association between the inputs image and the label. So after the model goes through the deck of flashcards, it is now well versed in classifying images with their respective definitions or classes. Explicit knowledge for YOLO-R is obtained from the shallow layers of a neural network. So a neural network might have multiple hidden layers, but in order to retrieve explicit knowledge from a model, those representations can be learned from this shallow part of the network. And this knowledge directly corresponds to the observations that are supposed to be made. Now that we have covered explicit knowledge, let's talk about explicit deep learning. Explicit deep learning was just briefly touched on in the paper of YOLO-R, but they mentioned that this can be achieved using detection transform, non-local network, and kernel selection. So these are just different techniques that they applied on their model to implement explicit deep learning. Remember earlier on, we mentioned that explicit knowledge is based on observation. Well, the authors essentially used scaled YOLO V4CSP for their explicit model. So we have said that we need a neural network or a deep learning model in order to extract explicit information. So in the implementation of YOLO-R, they just used the previous version of YOLO, scaled YOLO V4CSP as a backbone in order to extract the explicit knowledge. Next is implicit knowledge. And implicit knowledge, on the other hand, refers to the knowledge learned subconsciously, sort of like riding a bike or learning how to walk. It is derived from experience. So implicit knowledge is something that we learn subconsciously, and after some training, we are able to implement the task that is needed. So implicit knowledge can be defined as the detailed feature extraction from given data, whereas explicit is through raw feature extraction. So in order to implement the same kind of knowledge by using deep neural networks, the extraction of features from the neural network must be detailed rather than rough feature extraction that was implemented in the explicit deep learning. So for neural networks, implicit knowledge is obtained by features in the deep layers. So we have already talked about explicit knowledge, and we mentioned that we extract the features in the shallow part of the network in order to retrieve the explicit information. But in the case of implicit knowledge, we extract the features in the deep layers and not in the shallow part of the network. The knowledge that does not correspond to observations is known as implicit knowledge as well. So now that we have covered what implicit knowledge means, let's talk about implicit deep learning and how they implemented implicit deep learning in the YOLO-R model. So there is a couple of ways in which we can implement implicit knowledge. These include the manifold space reduction, kernel alignment, and more functions. Now, let's give a rough definition of some of the techniques used for implicit deep learning. So the first one is manifold space reduction. For this task, my understanding is that we reduce the dimensions of the manifold space so that we are able to achieve various tasks such as pose estimation and classification, amongst others. So dimension reduction is one of the techniques that is implemented in deep learning models or in machine learning in order to reduce the number of features or in order to reduce the dimensions of the network. And this can be implemented by using techniques such as PCA, which is another technique that is used in machine learning in order to reduce the dimensions. And so they implemented the same kind of technique so that they could be able to execute multiple tasks such as pose estimation or classification, as we can see in the figure. So one way we can do this is, in order to reduce the dimension, we can drop some of the unrelated dimensions or features that do not contribute anything to the learning of the network, and keep only the dimensions that are associated for a specific task. The second one is kernel space alignment. So they mention that in multitask and multi-head neural networks such as YOLO, kernel space misalignment is a frequent problem. As we have seen previously, YOLO has multiple heads. The head part of the network is a part of the network where we make predictions. And we make predictions in the YOLO model on different scales. So it is known as a multi-head neural network. And we face the problem of kernel space misalignment in the case of YOLO. So in order to deal with this problem, they perform both addition and multiplication of the output feature and implicit representations, so that the kernel can be translated, rotated, and scaled in such a way as to align each output kernel of a network. So what this generally means is that, as we can see from the figure, if we have an explicit information which is extracted by using one convolutional neural network, which is known as f theta, and then we have two different tasks that we are learning, or two different predictions or tasks, then without the alignment, without performing any kind of kernel space alignment, it's going to be very hard to make predictions. So what they did is, by introducing an implicit knowledge, which is represented by G, epsilon 1 and epsilon 2 in this figure, and the input for this network is, instead of X, we have Z1 and Z2. By introducing this implicit knowledge, we can align the kernel space for the representation that is learned from the explicit model. And this can be done by adding or multiplying the implicit knowledge with the explicit information. so that we can align each output kernel of a network. So what they mean is that this is essentially important for aligning features of large and small objects in feature pyramid networks. So they use the technique of kernel space alignment in order to align of some of the features that is learned from the neck part of the network, which is the FPN. And you can imagine that the amount of visual differences or disparity there are in pixels between objects that are far to those that are close to your camera. So in the feature pyramid network, we are learning objects at different scales. And when the objects that we are detecting are closer to the camera, they appear larger. And when they are very far from the camera, they are very small objects. So in order to reduce the visual differences or disparity that there are in the pixels of the objects that are far and that are close, we use kernel space alignment in order to fix that problem. And the third technique that they use to represent implicit deep learning is, in addition to the aforementioned techniques, they propose that you can also apply some operations for offset and anchor refinement as well as feature selection. So these are the three techniques that they implemented for some other functions that can be deployed in order to represent implicit deep learning. Meaning that you can apply different operations to perform different tasks, like either getting the class of the object, the bounding box, or the mask, amongst many other potential tasks. So to recap what we have learned so far, features obtained from the shallow layers are known as explicit knowledge, while features obtained from deep layers are called implicit knowledge. A unified network is a network that is a combination of both implicit and explicit knowledge. Now that we have learned how explicit and implicit knowledge work, we can combine both in order to create a unified model, which is shown in the figure below. And by using a discriminator, then we can get the output. So a discriminator is a network that is going to check whether the output from the previous model is correct or not. We have seen discriminators being implemented in generative adversarial networks, or GANs. So the authors combined both explicit and implicit knowledge in a unified network in order to perform various tasks. Early on in this paper, they do not mention what these tasks are, but if you browse through the experimentation section, they mention that they plan to do the following tasks like object detection, instance segmentation, panoptic segmentation, key point detection, image captioning, and more. So they wanted to create a universal model or a unified model that can be implemented for the different types of tasks. So how did they come up with this unified model, or how did they integrate the implicit and explicit learning? This leads us up to applying implicit knowledge into the unified network. And if we had to model a conventional network, it would look something like this. So for example, if we have this formula representing one output from a convolutional neural network, where X is observation, for example, let's say you see a dog, and theta is the set of parameters of a neural network, or these can be the connections or the weights. And f theta is representing the operation of the neural network, or the function. and epsilon is just the error term, then we get the output of y. So this can be taken as an explicit representation. So what is the problem by using just a conventional neural network or an explicit knowledge? The author states that when one trains a convolutional neural network, the goal is to minimize the error and to make f of x with respect to theta as close to the target y as possible, so that the prediction in the target could be as close as possible. There are some considerations that we can take in order to minimize the error. But now if we want to perform various tasks like object segmentation and pose estimation, for example, we would have to relax the error term to find the solution space for each task. If we want to perform a single task like classification or object detection, we can just minimize the error and that will be it. We don't have to do anything else. But if we want to perform multiple tasks using a single network, then just minimizing that error is not going to solve the problem. Since multiple tasks will have different feature representations, we have to come up with a different way. We have to relax some of the errors so that they can be a bunch of errors, but small errors. So that's called relaxing the error term. This currently is quite challenging to do, but a solution that the authors proposed is to rather model the error term epsilon to find solutions for various tasks by modeling an error. So we just model different errors depending on the different tasks, instead of just minimizing and relaxing the error. So we have already seen how to come up with the explicit part of the network. Next, we'll see how to integrate the implicit knowledge into the explicit part. This is where unified networks come into the picture. We can now expand our equation to incorporate the implicit model with g theta and the explicit error observation x together with the implicit error from z. So this g phi term is the one that's coming from the implicit part of the model, and this epsilon ex represents the explicit error from the observation x, and this is the implicit error from the observation z. And by adding this new term into the previous equation, we can integrate an implicit knowledge or implicit deep learning into explicit knowledge. So in layman's terms, it just refers to the representation of compressed data that makes up the implicit knowledge. We can further simplify the equation to this. So by using f theta of x, then we use an asterisk to represent different operations, and g phi of z. And by combining these two, we get an output y, which is going to be our unified network, where the asterisk represents some possible operators like addition or concatenation that combines the explicit and implicit knowledge, which is represented by f and g. So before we integrate the implicit knowledge into the explicit part in order to create the unified model, we need to know how to represent that implicit knowledge. So there is a lot more mathematics involved with the unified network architecture, but let's now move on to how the implicit knowledge can actually be modeled, which is shown in this figure. They can be represented in the form of a vector, So we have already seen that the input for the implicit part of the network is represented by Z, and in the case of explicit knowledge, we represent it by using the variable X, or it can be represented in the form of a neural network by using a Z vector and W. So the weights represents the neural network structure. Or it can be represented as a matrix factorization by using a bunch of Z vectors, and which is going to be used as a matrix by combining these vectors and factorizing it with a bunch of constants C. So it can either be a vector, a neural network, or a matrix. Finally, by combining all of the concepts that we have covered so far, we finally come up with the YOLO-R architecture. The architecture of this model, YOLO-R proposes a single neural network to apply implicit knowledge to three aspects, including feature alignments on feature pyramid networks, prediction refinement, and multitask learning in a single model. So this is the overall YOLO-R model, and these boxes represent the bunch of convolutional blocks that they're using as we go deeper into the network. And this is the feature pyramid network part. And we have seen previously that they have performed some feature alignment techniques in order to solve the disparity problem that is caused by different objects of different size. And this is just the techniques that we have discussed before being implemented into the FPN part of the network. And there's also the multitask learning, and finally the prediction refinement for the head part of the network. So multitask learning includes performing tasks like detecting objects and multi-level image classification and feature embedding. And the feature embedding refers to the process of extracting features and classifying them based on the attributes of these features. And finally, the prediction refinement part of the network is just enhancing the model by performing correction for the loss function that is used on the head part of the network. Finally, let's see how they implemented this new YOLO-R model and execute the training procedure. So they use the YOLO v4 CSP as their baseline model and introduced implicit knowledge into the model and trained it using the MS-COCO dataset. So the YOLO v4 model was used as a baseline, and they just introduced the new technique that they have introduced in the paper, which is known as implicit knowledge, into this YOLO v4 architecture and trained it on the MS-COCO dataset. So the way they tested the unified model was through an ablation study, which is just a fancy-ass way to say that they are testing one method at a time to understand the contribution of the component to the overall system. So if you're just testing a bunch of techniques and on a given model, and you want to understand the contribution of these techniques in order to enhance the overall system, that is just called an ablation study. So they followed the same training process as the scaled YOLO v4, in which they trained from scratch for 300 epochs first, and then they fine-tuned the model for 150 epochs thereafter. Then finally, the results from the model can be shown in this table. And if you look at the baseline, you can see the effect of the implicit model compared to the baseline. So this YOLO-R model, which is indicated under the bracket, is their model. And they compared it with other models such as scaled YOLO v4, efficient depth, swing transformer. And you can see that in terms of the mean average precision, the YOLO-R is comparable, but where it shines is in its frame rate. So as you can see, when we compare the average precision, it's kind of similar to scaled YOLO v4, so they didn't get that much improvement. But in terms of speed, which is the ultimate purpose of this paper, we can see that the frames per second has actually improved twice more than the scaled YOLO v4. So it's almost double the frame rate of scaled YOLO v4. So in order to perform the detection task by using scaled YOLO v4, it only took 16 frames per second. But in case of YOLO-R, it took about 30 frames per second, which is almost double than the scaled YOLO v4. But in terms of average precision, we didn't get any kind of significant improvement. So when they're creating a new model, in order for that model to be the state of the art, it has to prove two things. The first one is that it has to be moderately similar to the current models, so the current state-of-the-art model. And the second one is that it has to be efficient, or it needs to have low latency. So what they managed to achieve by using the implicit learning and implementing it inside the scaled YOLO v4 architecture is just enhancing the speed of the network. So if you look at the test run by the legend Alexei Pekovsky, they show an 88% in improvement in speed when compared to scaled YOLO v4, and a 3.8% improvement in average precision compared to PP YOLO v2. So as we can see from this graph, on the x-axis we represent the latency, and on the y-axis we have the average precision. So here the scaled YOLO v4 model is indicated by using a blue line, and the YOLO-R model is indicated by using the purple line. As we go to the left part of the graph, we can see that the latency is lower, which means it will have a higher speed. And we can see that the YOLO-R model is actually 88% faster than the scaled YOLO v4 model. And when compared to the PP YOLO v2 model, we can see that we have a gain of around 3.8% in terms of average precision. But in terms of performance, compared to the scaled YOLO v4, we can see that the scaled YOLO v4 is slightly more accurate than the YOLO-R model, but the YOLO-R model is much faster compared to the scaled YOLO v4 model. So that's all about for this video, and thank you for watching this channel.